So good morning, everyone. Today our topic is deep dive into query execution of Spark SQL. First of all, a little bit about myself. My name is Maryann. I'm a software engineer at Databricks. I also worked on different open source big data projects. I'm a PMC member of Apache Calcite and Apache Phoenix. So today this is going to be a 80-minute talk. I'll do the first part, and my colleagues Xingbo and Chris are going to take over later. Databricks is founded by the original team who created Apache Spark. We provide a unified platform that accelerates innovation by unifying data science, engineering, and business. Right now, our products is available in both Microsoft Azure and Amazon AWS. So our customers across different industries. Coming back to Apache Spark. In a few months' time, Apache Spark is going to roll out version 3.x, which includes a whole new component called Spark Graph. And all these components, like SQL, Spark ML, Spark Streaming, and new components, Spark Graph, as well as the lower-level APIs like data frames and datasets, are built on top of a unified compilation and execution engine, which we call Spark SQL engine. So the mentioning of Spark SQL is actually not only about SQL right now. It's this entire compilation and framework that transforms the user input into physical plans executable on Spark execution engine. So this gives us the benefit of being able to provide a wide spectrum of easy-to-use interfaces while optimizing and accelerating the execution in the same place, using the same framework, and even running the same set of rules. The Spark SQL engine is basically a query compiler and a runtime. So here's the workflow of the Spark SQL engine. It first takes user input like SQL datasets or data frames and turns it into a logical representation. Then this logical representation goes through the analyzer, which verifies the plan, resolve references, or some other stuff. Then it's the optimizer, which runs a whole bunch of logical optimization rules and transforms this initial logical plan into an optimized logical plan. Then it comes the physical planning stage, in which the logical plan is turned into a physical plan. And the physical plan is further converted to a DAG of RDDs and ready for execution in the Spark core. There's been a couple of previous Spark Summit talks that focus on the front end of the Spark SQL engine, which includes the analysis and optimization part of the logical plan. And if you're interested, you can follow this link to watch a previous talk given by in 2017 to learn more about the front end. But today our focus will be on the back end of this engine, which deals with physical planning, code generation, as well as the execution part. We'll also cover some specific topics about the execution, like task memory management, UDF execution, PySpark, vectorization, so on and so forth. So first, let's take a look at physical planning. As mentioned earlier, physical planning is basically what transforms a logical operator tree into a physical operator tree. One important aspect of physical planning is to choose the best physical strategy for a specific logical operation. For example, for joins, we have broadcast hash join, sort merge join, hash shuffle join, all kind of stuff. And these different physical strategies all have their own benefits and limitations. So, picking picking a good physical plan is a lot about, getting the right strategy for each operation. Another important thing is to take into account the physical traits of the distributed Spark execution engine, like how the data is distributed across the cluster. Some operators ask for specific distribution for its input and may generate output with a different distribution. In that case, extra physical nodes like a shuffle exchange will have to be added to the physical plan to satisfy this kind of physical trait requirement. And a result of this, logical node can sometimes map into multiple physical nodes. For example, if we have a aggregate, we usually end up with 3 nodes like partial aggregation, followed by a shuffle exchange, followed by a final aggregation. So this is a typical query example. And I'll use this example throughout my talk to illustrate different ideas. On the left side, it's a logical plan, which has scans on 2 different tables, table A and table B, and then the 2 tables are joined together. And then there's a group by aggregate. So after physical planning, it's turned into a physical plan on the right side, in which you can see the join has been planned into a broadcast hash join, and the aggregate becomes a partial hash aggregate, followed by a shuffle exchange, and then by a final aggregate. The scheduling of physical plan. Now we've got the ready for execution physical plan. How will Spark run this plan? Is the plan going to be run as a single job or as multiple jobs? And within each job, which part of the plan will run in parallel? So first of all, Spark will see if there's any scalar subqueries or what we call non-correlated subqueries, which usually appear in a word clause. And these subqueries will be executed as separate jobs. The same happens to broadcast exchange here, that has to be propagated. The broadcast relation has to be propagated throughout the entire cluster. And all the plan nodes that are dependent on such jobs will not start their own execution until the job it depends on completes. So in this case, the broadcast relation on the right side of the figure, which is a scan and filter on table B, gets to be in a separate job. And it will, and a join operation will not start until this job completes. Most other operators, like filter and project, can execute in parallel within each partition independently, as they don't require data from other partitions. There's a special operator called shuffle exchange, and on the other hand, it needs to move data around, from all the partitions across the entire cluster. So it breaks up the job into different stages. And in this example, we can see that in job 2, all the operators before shuffle exchange get to be in one stage, and the operator hash aggregate after the shuffle exchange executes in another stage. Then let's talk about code generation. So to start to talk about code generation, let's first start to look at the execution model of the Spark's physical plan. So the Volcano Iterator model, also employed by Spark SQL engine, is the classical evaluation strategy of analytical RDBM's query. Each operator produces a tuple stream, and a consumer can iterate over its input streams. So the tuple stream interface has one essential method called next, which is to get the next tuple, or say, to get the next row. To obtain the query output, the execution calls the next method on a final operator, and that one in turn calls the next on its input operator, and it goes on, and eventually we get, we end up with a propagation of the next calls. And a good thing about this model is that the abstraction is very flexible. It's super easy to understand and very easy to implement too. But this benefit also comes with a big downside, which is the lack of efficiency caused by this big number of virtual function calls. So starting from 2.x, Spark implemented a new execution model called whole stage code generation, which was inspired by HyperCodeGen paper from Thomas Newman. The new model will fuse a string of operators, and oftentimes the entire stage, into one whole stage code gen node that runs the generated code of these underlying operators. Now, that means Spark SQL engine not only generates code for the expressions on the physical operator tree, but also generates code for the entire tree along with the expressions. So this model is still a general purpose execution engine, just like the Volcano model, but without the Volcano model's performance downsides. Because the generated code, as shown on the right-hand side of, I mean, it's pretty much close to what's shown on the right side of this page, is rid of the virtual function calls and thus has enabled a lot more optimization opportunities for the Java compiler, such as putting data in the registers rather than on the stack, or loop unrolling, or SMID, etc. Now let's take a quick look at a comparison between the Volcano model and the whole stage code gen model. So the Volcano model drives the data processing from the final node, and each node pulls input stream from its upstream node. So it's pretty much a pull model here. So the whole stage code gen model, on the other hand, is more of a push model, and the iteration of the results starts right from the source operator, which is the beginning of the pipeline, and each node pushes its output to the downstream node. So again, here comes the example we used in the beginning, but this time with whole stage code generation enabled. And now we can see a number of operators in the same stage, like the scan, the broadcast hash join, and hash aggregate, have been grouped together and wrapped into a single whole stage code generation node. So how is this new model implemented in Spark? So first of all, we have this new node called whole stage code gen execution, illustrated in this diagram. And this node wraps the physical nodes in the same stage altogether. Like all the other physical nodes, this node also implements the old Iterator model interface, so it can interop with other codegen or non-codegen operators. What makes it different is that it compiles and runs the code generated by its underlying physical operators. So the next question becomes, how do the underlying physical operators generate code? The idea is that all these operators implement a code generation interface, which has two important methods, produce and consume. And the wrapper node whole stage code generation execution can obtain the generated code by calling these methods. One useful trick here is you can actually call query execution.debug.codegen on a data frame to dump the generated code. If you're ever interested, you can go try it out. So before we get into more details about a code generation implementation, we'll look at one other important property of the code generation model implemented in Spark. That is, there is no support for multi-dependency between the physical operators in a whole stage code gen node. Well, this can be seen as a limitation of the current model, but it also simplifies the problem. So we can always assume that the whole stage code gen node only contains a linear list of physical operators. But in the meantime, this list of physical operators can consist one or more pipelines. I'll talk about pipelines a little bit later. So let's first take a look at the case of a single pipeline in the host stage codegen node. The source operator, which is the beginning of the pipeline, will implement the produce method as a driving loop that produces the source data. This can usually be a table scan or an input RDD reader that reads from an existing RDD. And all the other operators in a pipeline are non-blocking operators like filter or project. And thus, they will not implement their own produce method, but instead they implement their row-level processing logic in the consume method. So if we look at the call flow on the bottom here, the code generation starts by calling the produce method of the final node, which is the host stage codegen node itself, and then it falls all the way through to the source node. The source node, in turn, generates a loop outputting the source data. Then it calls the consume method on its downstream node. And each downstream node generates its own consume logic and pass it on to the next node. And it goes all the way till it hits back at the very last node, the host state codegen node again, which will generate a return statement. So let's look at this example, which gives you a better idea of how this whole thing works. So this is a simple query of doing a filtering and projection on a table. So first of all, it starts by calling the produce method on the very last node, host stage codegen, and then it falls through to the very beginning of the pipeline, which is scan node. And the scan node does implement a produce method, which is to generate this loop iterating through the table contents. So right now we've hit the end of the produce call chain, and then the scan node starts to call the consume method on its downstream node, which is the filter that generates the condition block here. And the filter keeps on calling the consume method of its parent and generate this projection logic. And then it calls the consume method of the last node, the host stage codegen node, which generates the return statement. And that's the end. Now let's talk a little bit about multiple pipelines. So just like single pipeline in host stage codegen, there is a source operator in the very beginning, and it ends with a row iterator that consumes and returns the final output to the next physical node outside of this codegen block. And there's also non-blocking operators like filter or project or broadcast as join in the middle of a pipeline. The only difference here lies in the blocking operator that ends the previous pipeline and starts a new one, so which here is the operator for. So this can usually be a hash aggregate or a sort operation. The reason why blocking operators are pipeline breakers here is that they need to consume all the upstream output before they can generate new output for the downstream operator. So how do we implement the code generation interface with a blocking operator? So with the consume method, it just takes each row from the upstream operator and uses them to build the intermediate result. So for example, for hash aggregate, the intermediate result will be a hash map. And also the sorter in the sort operation is also the intermediate result. And the produce method has two parts. The first part is to call the produce method on its child operator, or in other words, the upstream operator, to generate a code that consumes the entire output from the previous pipeline in order to build the intermediate result. The second part is to start a new pipeline by initiating a new driving loop that iterates over the intermediate result. So here's another example which explains all, what I said. So this is about a hash aggregate example. So in this simple case, there's only two underlying physical operators in the host stage codegen node, the scan and the hash aggregate. So again, the code generation starts from calling the produce method on the last node, which is the host stage codegen node, which falls through to the produce method of the hash aggregate. Unlike non-blocking operators, which would again delegate the produce implementation to its child or to its upstream. So here, hash aggregate does implement its own produce method in two steps, as I mentioned just now. So in the first step, it calls the produce method of its child, scan, which generates the first loop here that goes through the input table and builds the intermediate result, which is the hash map, right? And the next step, it starts a new loop that iterates through the completed hash map and calls on the consume method of its parent. And it's the host stage codegen node. And then the host stage codegen node generates the return statement. So let's take another look at the join operation in host stage code generation. As some of you might have noticed, code generation is supported with broadcast hash join. And a broadcast hash join operator is fused together with other operators on the streaming plan side. Sort merge join also supports code generation. Given the fact that multi-dependency is not supported in code generation, the code generation implementation in Spark, so Spark has to do a little bit special handling with sort merge join node when planning code generation by putting the joins input into separate host stage codegen nodes. So as a result of this, the sort merge operator can only appear as the head operator in a host stage codegen node. So it can only be the source operator in a pipeline. And that's also why you are seeing quite a lot of host stage codegen node in this example. So before I end my part, I'm going to go through the limitations of code generation in Spark. So despite the many benefits of host stage code generation, Spark has also hit a few issues with host stage code generation, especially when the generated code size grows too large. One of the major problems is that in hotspot JVM of Oracle JDK or OpenJDK, once the bytecode size of a method has gone above 8,000 bytes, the JIT compilation will be disabled, which sometimes makes it even slower than doing the old Iterator model execution. The other problem is that the Java class format does not allow methods over like 64 kilobytes at all. But there's also a few solutions to these problems. The easiest one is to fall back to the old model if Spark ever finds out there's a generate method that goes beyond the size limit. Another way is to break up a method based on the known logic. So for example, we talked about this blocking operator. So in the blocking operator produce method, there's two different parts. The flow of building the intermediate result and the flow of consuming the result. So they're pretty independent from each other. They only share a few states, like very few states other than the intermediate result structures themselves. So they can be easily broken up into different methods. A slightly different but also similar approach is to put the consume logic of each operator into their own methods. So this is the end of my part. So if you have questions, you're welcome to ask them in the end of our presentation. So I'll hand over to my colleague Xingbo for the rest of it. Thank you.
Okay, so thanks for my colleague, Maryann, who will give a great talk about the front end and back end of the Spark SQL, the compiler part, and the code generation. So, let me introduce myself. Thank you. So let me introduce myself. I'm Xingbo from Databricks, and I'm a Spark miner. My interest area is majorly the Spark core module, which includes the job scheduling, the block manager, and the task memories, such stuff. So today I will talk about how does Spark SQL turns the physical plan into RDDs for execution, and the RDDs in turn will take the actions and generate the output result. So firstly, let's look at this example. So Spark SQL transform a user query into a tree formed by physical operators. That's what we call a physical plan. So Spark shall execute this physical plan and generate the query result. So how does this work internally? Let's explore together. First, let me introduce the concept of RDD, as known as the resilient distributed data set, which is the first initial concept of the Apache Spark program. Actually, RDD is a data set that represents immutable partitioned collection of elements that can be operated in parallelism. So from the point of view of Spark SQL, actually RDD is also an internal data abstraction that can represent the input and output data. Each RDD can consist of one or more partitions, and each partition may get fully retrieved from at least one single node. This also means we can execute physical operators on different partitions of the same RDD at the same time. So in this way, we can explore parallelism. So let's show how the physical operator actually works. Each physical plan is generated from one or multiple physical operators. At execution time, we generate the result of our physical plan by generating the result of each physical operator and chain them together in some specific way. Here, we show an example of how to generate a result of a physical operator under Volcano Iterator model. Basically, the physical operator has to provide a do-execute method, which provides a code snippet that consumes the input iterator and produces its own. In this way, we execute a physical operator and generate a RDD that represents the output data. So let's look at this example. The physical operator filter provides a do-execute method that accepts the iterator from the input RDD, and for each input data it reads. If the data satisfies the condition, it appends the data into the iterator of the output RDD. Also, we can see that it's easy for the filter operator to do execution on different partitions of the same RDD at the same time. On execution time, we explore parallelism at the physical operator level by putting together the physical operators that can be executed on the same partition. Consecutively, operators of such kind are grouped into one stage, and the stage boundary is called a shuffle, which acts as a sync barrier across all nodes. That means a stage has to wait until the stage it depends on to be all finished before it can start executing. In this example, we turn the physical plane into three stages, separated by shuffle exchange and broadcast exchange operators. So among these, the broadcast exchange operator generates a new job, while the shuffle exchange operator generates a shuffle as a stage boundary. When we start to execute a stage, we will start a task set. A task set is a set of tasks. Each task performs the consecutive operators in the stage on a partition of the input RDD that is on a local node. The task set is responsive to start and monitor and update the status of the task in the set. So if the stage execution is triggered multiple times, then there may be multiple task sets running at the same time to generate a result of the same stage. This also gives a way to accelerate the execution time of the Spark stage. So let's see an example. Spark tracks whether a stage execution has been finished on each partition. Thus, when a task set is triggered, it only launches tasks on those partitions that haven't finished the execution yet. This approach can help us save much cluster resources, especially when the cluster is not stable, and you may have to retry many times to complete one stage execution. So in this example, there are 4 partitions in the input RDD, and we have finished the execution on partition 2. So when we start a new task set for the stage, the task set 1 only launch task on the missing partitions, that is the partition 0, 1, and the partition 3. So in another try, in another stage execution, the stage has finished the execution on partition 1, partition 2, and partition 3. So the new task set started, the task set 2 only need to start one task to execute on partition 0. And when it finishes, it will mark the stage as finished and continue to work on its children stages. So how does Spark run a task internally? Actually, Spark provides system resources in the form of executors to run tasks. Each task runs as separated thread inside the executor. So you can imagine that the executor is actually a container, and it starts many threads, and each thread contains a task that's running in it. So each executor has its own CPU cores and memories. The number of tasks that one executor can launch at the same time is controlled by the config spark.task.cpus. So in this example, the executor can launch 5 tasks at the same time. Since the executor contains 5 cores, and each task will require 1 CPU resource. So when each task has finished, the executor will update its status, and we may launch pending task on the free slot. In this example, the task 0 to task 4 are running on the executor, and task 1 has just finished. So another schedule iteration is triggered, and when pending task, the task 5 is scheduled to run on the new free slot. We all know that Spark delivers correct result with a least time cost. Actually, Spark also offers failure-tolerant mechanism to be resistant to transient or persistent cluster failures. Unlike most MPP analyzed databases and several of the new low-latency engines proposed for MapReduce environments employs a cross-grained recovery module, where our entire query has to be resubmitted if a machine fails. Actually, this works well for short queries where a retry is inexpensive, but faces significant challenge for long queries as the cluster resource scale up. So on the country side, Spark uses a mid-query recovery model, which tracks the series of transformations used to build them to only recompute the lost partitions. So normally, a failed task can finish successfully on a retry run. On task failure, Spark shall record the failure count of the task and retry the task if the failure count is less than the max task failures it specified. And it observed the failed count has exceeded the threshold, then it means there is something goes wrong permanently, so it will abort the stage and the corresponding jobs. Fetch failure is another issue. So what is a fetch failure? Fetch failure is when you want to fetch the result from a previously finished stage and you found that, oh, the shuffle file is not there. It may mean the file is broken or the node has goes down. So when we see a fetch failure, when we see a fetch failure, it is most likely that some RDD partitions are lost. So instead of retry the failed task, we just retry the stage. So in case of fetch failure, we just don't count the failure into the task failure count and just retry the stage. If the stage failure is less than the max stage failures specified, and if the stage failure exceeds the max stage failures, then it will just abort the stage and the corresponding job and request the user to submit again on a different cluster. It will also optionally mark the executor or the host as lost to avoid further attempts that will also trigger the fetch failures. Okay, so long for this session. And in next session, I will give a talk about the memory management, and also my colleague Chris will give talk about the PySpark and the vectorized readers. So thank you. Let's have a break for 10 minutes. Thank you.